Hello everyone, it's already 10 o'clock, so we can start the second day of an anniversary MIDI conference. My name is Cezary Bile and I'm the head of a laboratory of interactive technologies at the National Information Processing Institute in Warsaw, Poland. And during the conference, I'll be making sure that everything goes smoothly. As you probably noticed, this year the scientific program of the conference was split into 3 days. Last year, we, thanks to your help, conducted research trying to find the most effective ways of carrying out a remote conference. And one of the findings that we came across was that it's better to split the program of the conference into 3 days. Before we had 2, because the shorter session eliminate at least partly Zoom fatigue. We all know it from working remotely, and also it is easier to combine the participation in the conference with everyday responsibilities at work. And so this is what we decided to do this year, and the conference, the scientific program of the conference will take 3 days. And if you are interested in the topic of this research, you'll be able to read more in the paper that will be published on the CHI conference this year, and it's entitled "How to Organize Engaging Online Conference and Escape the Zoom Rectangle." We also planned several activities created to increase your satisfaction from the participation in the event. You may also know it from last year if you participated. And let me go briefly through these activities. The first one is a virtual participants map. You can find it on our website. The idea is to mark the place from where you connect, and in the effect we'll be able to see all the places around the world when scientists participate in our conference. The other thing is Zoom background generator, the one that you may see behind me right now. So you can use the script on our website to generate a similar background, and I also encourage you, of course, to do so we can create an identity for our conference. And last but not least is a virtual mural. Last year we had a similar activity. You can see the mural from the last year. It's not in its final form from what I see, but I hope that we'll be able to create something as interesting and as engaging as this mural from last year. And for the activities to create engagement and the sense of being together, because this is what we think is very, very important, we also prepared some entertainment for the conference, but I will talk more when the time is appropriate. Coming back to scientific program, this year we have the 2 special presentation sessions this year. It is the first time that we have a special session, and the first one is called Interacting with Virtual Reality Applications, and the second one is Advances in Collaborative Robotics. Both of the sessions were organized by scientists from Warsaw Technical University, Jakub Morzaryn, Jan Klimaszewski, Krzysztof Wildner, and Anna Sibilska-Mroziewicz. And of course, they will be chairing this session. On the last day of the conference, we also have a closing keynote by Leslie Shannon from Nokia, and we announced the winners of the Best Paper Award, which this year is also funded by National Information Processing Institute and Polish-Japanese Academy of Information Technology. Speaking of papers, we also plan to publish proceedings of our conference with Springer, and same as last year, we hope that it will be available as in the open access format. We all know that it's very important to increase the reach of our work. And it's really easier to promote your work in the publications that are available as open access. Okay, so I think that's for the beginning of the day. That would be all. We can move now to the first session in our agenda for today, which is machine intelligence session 1. And the this session would cover such topics like predicting music, recognition of shoes, playing arcade fighting games, and also recognizing vehicle logos. Speaking of vehicles, I always wanted to have a DeLorean. You probably may know this car from famous movie series of movies. However, later I decided that it's not a good idea, because I'm afraid that if I bought it, I would only travel it from time to time. Okay, so going back, the chair of the session will be Dr. Rafał Jóźwiak from National Information Processing Institute. Are you with us, Rafał? Hello?
Yes, hello, Czarek.
Okay, great. We can hear you well, so the floor is yours.
Okay, thank you very much. I'm very proud. That's a great honor for me to become chair of that session. So one more time, welcome everyone during our first session during the second day of the conference. Shortly, what will be the plan for our session, because we have the online form of the conference. We have the pre-recorded presentation, so every presentation will start with a movie, which we will display and we will see. Then I will kindly ask the presenter, after showing the movie with presentation, to become also visible just like me. And we will start a short question and answer session, yes, because of the online form, we decided that during the session, we will accept questions in form of question on chat. We won't have any oral questions. So please, everyone which now available with us, if you have some question, please on chat, prepare such a question during the presentation. I will try to moderate all that question and ask that question to the presenter. After finishing our whole session, there will be a special dedicated breakout rooms in which all of you will be able to meet the presenter and ask additional questions personally and discuss all the questions, all the problems in detail. Okay, so I think we can start our session. We will start with the first presentation. The title for the presentation is Light Fixture Position Detection Using a Camera.
Hello, my name is Wojciech Leśner from Czech Technical University in Prague, and today we present interdisciplinary research combining computer vision with stage light design to detect light fixtures automatically. Think about theater lighting, where light fixture positions can frequently change, large-scale dynamic light installations, or perhaps the event industry, such as concerts. In all these cases, we have multiple light sources that we need to control centrally. To create more advanced light effects, such as a light wave traveling through numerous lights, we need to know the positions of the light sources. Traditionally, light positions are either planned beforehand or time-consumingly mapped manually. We have developed a system using a regular webcam to detect light positions automatically, speeding up and automating the data acquisitions needed for the light design. Our system can control the connected lights via ArtNet protocol and take photos of the stage with the lights on and off repeatedly to determine their position. The result is the DMX address and position pairs in JSON and CSV table format that can be used in the light design software such as Matrix, Touch Designer, LightGems, and more. We also included graphical user interface to verify the final result and allow users to define the region of interest in the camera image with masks and perspective deformation. We have successfully tested the system with independent LED modules as well as multiple LED strips. Furthermore, we have compared various camera resolutions to see if the accuracy will improve. In the end, we found that the camera resolution is not a significant factor in the accuracy of detection, as there was no significant difference between 640 per 480 pixels compared to 1920 to 1080 pixels resolution. Our system, in its current state, has some limitations. First of all, currently, we only care about the 2D position. That is fine as long as your lights are all hanged from the ceiling at the same height or fixed on the wall. However, if you have multiple layers of lights or more complex compositions, we would need a 3D position. In future research, we plan to solve it using the stereoscopic camera to get the distance to each light as well. Another problem we have encountered was light reflections. We have partially solved the problem by providing the masking tool to the user to limit the reflections from surrounding walls or floors. But if you have a reflective ceiling such as chrome plate or similar surface, our system will need help to get accurate positions. We plan to implement shape recognition in these cases to aid the detection process. To conclude, we have created a proof of concept for automatic light position detection that can speed up the installation time and, more importantly, allow light designers to produce more organic designs and prototypes rapidly. Thank you for your attention.
Okay, thank you very much for that presentation. Can we ask the author to join to us?
Hello, good morning.
Hello, good morning, welcome. Thank you very much for that presentation, very interesting presentation showing that system, which I think possesses very practical usage and lots of practical applications which you presented. I'm looking for chat to see whether we have some questions for the audience. I'm waiting, looking, maybe someone will have some question to the presenter. No, I can't see any questions, so I will give some question because you are using, if I could understand, you are using a normal video camera, yes, to record the lights. At the beginning, during the presentation, yes, we were showing the lights, that wave with lights going very quickly. What is the frame rate you are using? Yes, is it fast enough to catch such a quickly changing lights?
All right, so let me clarify here. There are two parts actually in the software, and the wave you have seen in the video, the animation, the actual animation that goes from left to right through all the lights, that's basically a test pattern that we integrated into software. So immediately after the calibration, after you have got your data, your pair positions and DMX addresses, you can verify that indeed it's working. So that's why we included this animation. But it is meant that you use these data in your own light effect software. So the animation is there only for you to verify it. It's not the part of the calibration process. And the speed that we can capture data, it's actually not that bad, but we are not limited by the web camera frame rate itself, but rather by decaying speed of the light from the reflectors that you are using. So it can be very fast actually. So if you are using LEDs that you can individually control, then I say like you can achieve like no problem 60 frames per second. But if you are using some theater reflectors, for example, that are using classical indecence light bulbs, then you have to wait longer time to be sure that the light is already turned off when you are capturing the image.
Mm-hmm. Okay, and what are the possible application, what the type of application you see the most promising in that methodology, in that system?
So we already use this system, and something that would take you a few hours of your time manually marking where the lights are and making sure that you can produce such light animations as the wave traveling from one side to the other, as we saw, is now basically, you know, they've done in 5 minutes, and on top of that you don't even have to be there. So it can be supervised, it can be done remotely, so you have a technician on site that will just point the web camera for you. You can run the software and you have immediately the plan of the stage. So that's one use case, to actually speed up the installation process. But for me, more important feature is that now we can prototype more rapidly, more organically. So if you are a light designer and, for example, you are in theater and there are, you know, lights positioned somehow, then, you know, you can change stuff. You can move the reflectors to different positions, then just like run calibration process very quickly. And then again, you can try the animation and see, is it better, is it worse? So you can change things based on that. And previously that wouldn't be possible because it would take a long time to achieve it. So you would spend half day away, then you would came back, and even after that you would have to say, okay, is it better, is it worse? Now you can do it not real time, but almost immediately. So that's an improvement that we are offering.
Okay. Thank you very much. That's all from me. Very interesting presentation for the beginning. Very good open. I can't see any other question on our chat. So thank you one more time for your presentation.
Okay, thank you very much.
Okay, dear audience, we can quickly move to the next topic and to the next presentation. The next presentation title is Improved Vehicle Logo Detection and Recognition for Complex Traffic Environments using Deep Learning based unwarping and extracted logo recognition in varying angles. Let's see the presentation.
Hello, and welcome to the presentation of publication of the paper Improved Vehicle Logo Detection and Recognition for Complex Traffic Environments using Deep Learning-based unwarping of extracted logo regions in varying angles. Here is a brief introduction about the authors of this paper. Traffic situation is demanding innovative solutions for effective monitoring and management given the complex nature of the urban scenarios. Intelligent traffic monitoring and management system is a growing research area, which includes detection, recognition, and fine-grained classification of vehicles, automatic license plate recognition, and various kinds of traffic analytics. The fine-grained classification of vehicles is the process of categorizing a vehicle into its make and model. Many techniques are used for this classification, some by considering the whole vehicle or others through a certain area of vehicle, for example, logo. A vehicle logo is a distinct appearance-based feature which is an important part of this whole process. Logo recognition plays an important role in the scenarios where authenticity of vehicle's make is doubtful. For example, the scenario where a stolen vehicle license plate is replaced with another one, or when a license plate is obscured or illegible, which affects the readability process in ALPR systems. Identification through vehicle's logo is a challenging task due to its smaller size. Detection and recognition of small objects is a fundamental challenge in computer vision and is a growing research area these days. Many researchers have achieved high performance for small objects detection using convolutional neural networks. However, these small-sized logos are also affected by background clutter and noise. Similarly, most of the times logos is blurred and not properly illuminated, and even not visible due to rainy or snowy weather, which causes difficulties in features identification. The main contributions of this paper are highlighted as followed. An offline vehicle logo detection and recognition approach that uses video feeds acquired through low-resolution surveillance cameras for authenticity validation of vehicles. Improved logo detection and classification based on a modified state-of-the-art license plate detection network. Post-variance analysis to identify the varying angle on which the proposed approach can work. A publicly available vehicle logo dataset VL10 containing logos of 10 commonly used vehicles, makes, and models. Let's talk about the working methodology. Step 1 is unwarping the model IWPodNet. Improved warped planar object detection network detects four corners of vehicles' license plates and unwarps to eliminate perspective issues. The model was modified to extend the ROI by a variable to also include vehicle logo region, while assuming the logo placement is always on the top of the license plate. After extraction of ROI, it was then unwarped to fix perspective issue. Step 2 is logo detection model, which is YOLO V5. This research utilizes the YOLO V5 P5 medium-sized model for logo detection. Due to low classification accuracy, the model was used to detect the presence of logo only. The unwarped images from previous step is then fed to YOLO V5M model for the detection of logo. Step 3. Logo classification model EfficientNet. This research work trained EfficientNet on logos in the proposed dataset. Firstly, all images were cropped to the logo part, which were then used for training the classification model. In testing phase, once the logo is detected in the ROI, it is then fed to the classification model as an input. It then classifies the logo into its respective class. The lack of a local dataset can become a huge challenge when performing these tasks for any particular region with a specific complex traffic environment. A local dataset of vehicles, VL10, is developed where logos are either prominently visible or partly visible due to varying angles as in surveillance environment. The logos are categorized into 10 different vehicle classes. A total of 550 images per class were selected to form the training and validation sets respectively. The data augmentation was then carried out by adding blur and noise to each image. Therefore, the total images per class became 1500 and 150 for training and validation sets respectively. This figure shows the sample images from VL10 dataset. Different surveillance scenarios have been chosen for test of the proposed model pipeline. These include video streams from toll control, law enforcement, parking lot access validation, and dashboard cameras. Moving towards the different approaches that we have used for comparative analysis. Approach 1. Without IWPodNet, using YOLO V5 for both detection and classification. YOLO V5 model was trained on VL10 dataset for both object detection and classification tasks. All test scenarios were first passed to this model to get baseline accuracies. Approach 2. With IWPodNet using YOLO V5 for both detection and classification. The detected vehicles were passed to IWPodNet for the ROI extraction and unwarping. It was then passed to the YOLO V5 model, which detected and classified the logos into their respective classes. Results were improved to a certain level. The highest improvement shown is in the law enforcement test scenario. This is due to the fact that this test set has side camera viewpoints and IWPodNet has helped to unwrap these side views really well. The lowest improvement is shown by parking lot access validation test set, which is apparently due to the fact that camera viewpoint is already frontal and the license plates are not very oriented in this case. Approach 3 with IWPodNet using YOLO v5 for detection and efficient net for classification. After extraction and unwrapping of ROI through modified IWPodNet, it was passed through YOLO v5 model for logo detection. ROI was then passed to the efficient net for classification of detected logo. Considerable improvements in the results were observed. Highest classification accuracy was produced in the case of parking lot access validation. The margin left in this case is due to the inclusion of night images in the dataset where the logos are not perfectly visible and the use of streetlights create the issue of reflection. Approach 3 stands out from the other two approaches. Post-variation analysis was conducted to determine the capacity of the proposed model to detect logos accurately at varying angles. Some images were captured in the daylight similar to the settings in parking lot access validation dataset. Foes were categorized by comparing the oriented bounding boxes and rectangular bounding boxes of license plate. Proposed module was able to detect logo in the range of 0 to 30 degrees, while it was mostly undetectable beyond this range. In the range 0 to 10 degrees, the module's logo detection mean average precision was 0.91, while the classification accuracy was 0.97. In the range 10 to 20 degrees, the module's logo detection mean average precision was 0.85 while the classification accuracy was 0.90. In the range of 20 to 30 degrees, the module's logo detection mean average precision was 0.80 while the classification accuracy dropped to 0.75. This paper focused on surveillance environment and presented a novel method of detection and recognition of vehicles' logos at varying angles. A new dataset VL10 based on local environment settings was also proposed. 3 different approaches were proposed based on 4 surveillance environments and their comparative analysis was also discussed. Post-variance analysis was also performed to determine the orientation limits to which this approach can work. It was observed that the proposed approach worked best in the 0 to 30 degree angle range, while it was mostly undetectable beyond this range. The proposed technique significantly improved logo detection and can therefore be used in offline surveillance environments. As part of future work, the deep learning architecture can be optimized to detect and recognize vehicles' logo in real time. Similarly, a completely new deep learning architecture can also be designed particularly for this task. That's all. Thank you so much for your time.
Okay, thank you very much for that presentation. I see the author is available with us. Hello.
Hello, everyone. Good morning.
I'm looking quickly for our chat. Do we have any question? I can't see any, but I have, of course, the question for you prepared. You mentioned at the end about the possibility to moving online with that idea. The question is about the problems which might happen when we are working online. First, of course, about the speed of the recognition. Is it possible easily to reach them online? But the second problem is that I think the logo is very small, which was mentioned. And in case of online, what do you think about the problems which might appear with light reflections from the logo? Very often the logo is silver, of course, so it can produce a lot of reflection when it's small. You think it will be a big problem for that system online?
All right, so this paper is basically mostly focused on the offline implementation of this scenario. That's because this is a very small part of the whole scene. Logo is already like it's installed with on a vehicle, which is already very small part. Like for example, in the case of tall plaza or tall scenarios where the vehicle is already very small. So we have mentioned this in our paper that this is an offline proposed technique, because what we are first doing is first identifying the vehicles and then extracting out the logo region and then identifying the logo, which logo that is. So this is basically why we are saying this is an offline proposed module, because it takes around 20 to 30 works on 20 to 30 frames per second. So yep, and as you talked about the shiny surface of logo, this is the basic and the most major problem of what we faced while solving this problem, because light reflection, whether it is daylight or night light, it always presents challenges to detect a logo. So and obviously the size, as you see that we are working on the surveillance environment mostly, which becomes even more difficult to handle, because the logo appears even more smaller in such scenarios. So yes, this is the biggest challenge. The surface is always silver, mostly silver or shiny. So this is the biggest problem while dealing with such problems. Yeah.
Mm-hmm. And the second question is related to the analysis which you made with angels. Yes, the limitation no lies about the system works between 0 and 30, as you mentioned. Yes, the picture which was also in the paper presented, yes, show also a small example with the higher degree, about 40. Which theoretically, if I look for that picture, the logo is still visible. Of course, that angel is quite big at that moment, but the logo is still visible. Is it possible in future to also improve the angel?
Yes, so we are working currently on this problem to improve the accuracy on even greater angles, where currently it is impossible to recognize it. But if you just look at the logos beyond 30 degrees, what happens is that it just takes the position where the computer is basically doesn't perform well, because for example, if it's Honda, let's say, so the both lines of H, this looks something like that. They hide beneath each other. So currently it is not possible by our proposed technique to mostly recognize the angle beyond 30 degrees, but yes, we are working in improving the efficiency and accuracy of the model.
Okay, thank you very much.
Thank you.
We have one question from the audience, so I will quickly take that question. How does logo detection compares to trying to detect particular car models based on shape, for example? I understand that your approach is more hood-proof. I think you also see that question on the chat.
Yeah, I can see that, but can you please clarify your question a bit, because how does logo detection compares to trying to detect particular? Okay, so so basically what we are doing is not basically a more generic fine-grained classification. We are just detecting the logos. For example, if it's Honda, it could be any model of Honda. What we are trying to do is just to detect logos. We are not going to with a specific model recognition of the let's say Honda it is. So this is useful, especially in the scenarios where let's say there's a stolen car, and let's say the license, for example, license plate is swiped, but we can have still an idea about the car through its logo and other features, but we are not really going into the model recognition, exact model recognition, more fine-grained model recognition of the logo of the car. Hope that answers. Yeah.
Thank you very much. Thank you for that question. I can't see at that moment, I can't see any more questions. So thank you all the authors for that impressive presentation. I think later there will be also time in our breakout rooms for more discussion in case other questions appear. Okay, thank you one more time.
Thank you.
Now we move to our third presentation today during our session. The title for that presentation is Predicting Music Using Machine Learning. Let's see the presentation.
Hey everyone, I'm here to present about predicting music using machine learning. And this gives a very interesting perception to how things can be driven using machine learning and AI in the modern world. So let's just think for a moment, if AI could produce exact music with the lyrics you always wanted, that feeling that has so many benefits around, and you don't need to worry about copywriting, you don't need to worry about any kind of taking any drummer with you. If you just want to create a tune, you can just go ahead and do that. The research, let's talk about that. So the intricate temporal prolonged sequences seen in music make it a perfect environment for the study of prediction. Melody, harmony, rhythm are three examples of structural elements found in music. This research incorporates music excerpts, prediction by understanding structural details using Markov chain and LSTM modeling. The novel approach compares state-of-the-art algorithms by predicting how a musical excerpt would continue after being given a small input. In some cases it continues for lifetime. So to compare the variations in prediction and learning, different learning models with different input tuning and parameters are tested upon, and different feature utilizations were used. So this algorithm envisions multitude of uses, as I already discussed some of them, including next generation music recommendation systems that can predict music that are very similar to each other using intra-sequence matching, a pitch tone correction, amongst others, by integrating with different advancements in deep learning, computer vision, speech techniques. So the benefits of this, you can always rely on such kind of systems to produce music as you want. You don't have to basically rely on anything specific, that if you want to have a jazz music along with maybe just a systematic rhythm, you can just go to the system, have it play. Maybe you can give jazz input and some pop culture input and see what it produces. If it doesn't suit you, you can choose different genre, different music styles, and then see how it transforms that small piece of music into a beautiful art. So why do we care? Even though the Western music scale has only 12 notes per octave, it encompasses the vast majority of music we are familiar with, and everyone knows Beethoven and Beyonce. So the past 10 years have seen an increase in interest and diversity of various methods for algorithmically creating music using a variety of learning techniques, and can deep learning models be used to study and utilize the genius of Mozart or even Beethoven? That's the simple question, but tough to answer. Now, while music has attracted a lot of attention, research on music prediction hasn't. So in this research, we are just trying to have a music snippet. Predictions are made for following n musical occurrences, and that you can set that to infinity if you wanted to. The actual musical occurrences are then contrasted with the predicted music, and then prediction is created using a scoring system. The experiment leaves one wondering on whether music prediction or music generation is trickier, and that's a very interesting domain that it just opens up to. So feature representation, let's talk about feature representation first. So the basic music notation, the fundamental component of music and foundation from which all chords and melodies are built, are notes, and each note has a pitch and a duration. So pitch is essentially the note's sound frequency, and the MIDI music file system can store 128 different pitches. Quarter note lengths are used to measure duration, which is the length of the note. When several notes are played simultaneously, they form like chords. And since only one note is played at a time, monomorphic music like lacks chords, and polymorphic like monomorphic music systems, like if they're combined, they have chords. So let's talk about like what are notes and chords, like how are they represented. So each node has like encoded as an integer ranging from like 0 to 128. And due to the fact that notes have 128 pitches in the MIDI file system, it just makes it a lot more easier, you can say, or even like a bit complex in that fashion. And the duration representation, so that's like the duration for each quarter length of note. So number of durations may be like not set, or in principle like it may be like very vague. Duration length is typically spread amongst like a limited set of choices, and all of the training data's duration was sampled and dictionary was built, and it was taken care like that the random sampling was well enough that like all kinds of music could be incorporated into the training process. Combination representation, combination of note pitch and duration as tuple was represented initially as pre-process step. For instance, the tuple was used to represent a note with a pitch of 60 and duration of 1 quarter note length. Interval representation, so note intervals were used in the final input representation, and like pitch difference was used between two notes, like what pitch difference, what amplification difference is present between like two different tunes. And for instance, like the pitch difference between note 60 and 65 is 5 semi-notes. That's how like you tell it in the music world. And talking about methods in modeling, so Markov chains were one of the earliest models utilized for music production, and a first order and second order Markov chain was trained and evaluated, and it was like separate training sessions were used for notes and duration, so that like we don't mix and match the models. And this model could be utilized with inference modeling like restrictive inference or like beam search. LSTM modeling, like a forest of long short-term memory network, was also used for next set of experiments. Single network with multivariate input made up one model. Similarly, like you can see like the right side diagram represents like a LSTM model with like multivariate modeling. So the encoder decoder model is basically like two different models for the notes and durations, and as well as like single multivariate model was trained. So the parameter matched those of the LSTM model as we like saw, and the longest prime sequence in the training set served as the input. Inference modeling, like that's another technique that just was explored. So prediction was performed using the common beam search algorithm with beam sizes ranging from K2 to K4, and only the nodes from the prime part were used for the constrained inference, and the following node with the highest score, like that was given the best scoring amongst the system, and that was chosen as the default output. So some other techniques were also followed, like transposition, and it was a method which was used to increase the uniformity of the input data. In music refers to process of raising or lowering notes and chords by a fixed distance, so that like you can hear like a symmetric sound. And yeah, like what we got, like just drilling into that, so it like Oblivion, like this is one of the good music that was generated by the AI, and like for music lovers this is like endless music, so it will always be there, and it won't be like as long as you wanted it to be. So it changes pitch, notes and amplification from time to time, like mostly reflecting time of the day, and it was trained like using all different kinds of like jazz, pop, harmonious music. So like when listening, it feels like sitting by a river. It's like always the same river, but like you hear different sounds of it. So it's like for, as I said, like for people who just want to listen to the same music, and it doesn't change like just randomly in between, but with time it shows that effect that something is changing and like things are getting distorted, so you would hear the difference. It's really nice, like yeah, so kind of a soothing effect. So yeah, just move.
Okay, thank you for the presentation. Let's welcome the author of the presentation. Hello.
Hey.
Okay, I'm looking for our chat. Do we have any question for our next presentation? Very interesting presentation related to problem of application of AI in topics related to music. That's a very attractive field of research. In your work, as I observed, you applied the LSTM model. Yes.
Yeah.
Have you considered other architectures maybe to that problem, or maybe some improvement to LSTM model, or maybe what are the plan for the further development of your research?
Surely. So, like for models, like we were considering like three, four options. So, like the first one I was seeing is like Markov chain modeling, and that's like one of the earliest models utilized for music production. Like because it just is so good at catching like sequences of different elements coming together. And the variants we were using was like a vanilla model. So that was like the first order Markov chain modeling, and also the second order Markov chain modeling. And like it was used for training and evaluation. Like separate training sessions was like held for notes, chords, and like durations, intervals. So this model could have been like utilized, but it was like a very basic approach. So like I went ahead with the LST modeling, and a forest of like long short term model, like that's what the LST model stands for. And it was used for like various sets of experiments. The single network with like multivariate input are made up from one model, like both nodes and durations. And for the like respective authorities of like intervals between different nodes, it was established that nodes and like durations have a significant relationship between like prediction of sequences of like tunes. And input layer, like it was like a 64 dimensional embedding layer, and 512 like hidden units LSTM layer. So normal batch processing was like possible, and dropout layer was like had a rate of like 0.3, where the layers were present in like both modeling. And then like one other thing was like LSTM encoder decoder model. So two different models for the nodes and duration, again like in a similar fashion, was here used as well. And the longest prime sequence in the training set served as the input sequence for the like next train sequence. And then the graph of the multivariate encoder decoder model, like that was like a bit I explained that during the presentation. One other thing I was thinking, like for maybe the future of this research study, is like going forward with like inference modeling, because prediction like was performed using common beam search algorithm, and that could have been like much better if we could have done it with the inference modeling. So with the like with better infrastructure and things like that, it is possible. And only the nodes from the prime part we can use, and also we can incorporate like secondary parts to get like a better constraint like sequences. And yeah, so
And in your experiments now, up to now, have you focused on some special music genres during that experiment?
yeah, so I just used like an amalgam of different like music notes, and just wanted to see what we can get out of it. And it just seemed like it was like oblivion music. So it just started. So it in that music, like you can just keep on listening. Like if you get bored with certain tunes, it will change like according to the time of the day, like the your mood, like the sequence that you wanted to say. So suppose like if you are just throwing in like 10 different songs from 10 different like genres, so it will just start like reading it through, and developing like a very basic tune, I would say. Like it's not something that is made up of like 10 different instrument, but yeah, like 2 3 instruments are played very well. And it was sometimes even better than what was like originally like formed in some cases. So it just kind of like was a soothing effect, kind of like if you're sitting in front of a river and it's the same water, but like the sound changes every now and then. So it was a really nice tune that I showcased.
Okay. Thank you very much one more time for the presentation.
Thank you.
Okay, dear audience, let's move to the next presentation. The title of the next presentation is A Novel Process of Shoe Pairing Using Computer Vision and Deep Learning Methods. Let's see the presentation.
Hello everyone, my name is Przemysław Buczkowski and I would like to talk about our project in which we used machine learning to pair shoes. I work in National Information Processing Institute, and what we do here is, amongst many others, machine learning. In 2020, Vive Textile Recycling approached us and said, hey, we have a lot of hardware, including building size conveyor belt, which can transport a lot of items, and also cameras who can photograph those items, and also some programists who can integrate them, but we are lacking expertise in machine learning. Can you give it to us? And we did. And also National Center for Research and Development came and said, oh my god, this is brilliant, we want to fund this. And they also did. So this is the scope of our project, and now I'm moving to the topic. So the idea is to create a system which can be fed with some batch of shoes, population of shoes, and do some smart processing of them. For example, pair them or describe them in many categories. But describing is outside of the topic of this presentation, so we are focusing basically on the pairing. This is the architecture of National Information Processing Institute part, actually the smart part of this project. So given our project is machine learning project, we needed some data to train our models on. So we constructed a web application, Shoe Label, which used human annotators to annotate and hand label the data and store it into a persistent storage. Then data scientists could train those models and on the hand labeled data and store this into the storage, and later Shoe API was used to serve the knowledge of those models to the Vive itself. This slide presents screen from the Shoe Label application. You can see the first shoe, second shoe, each one having 3 images of different sides of the shoe, and also a number of questions which were asked to the user. At the time of the study, we had 40,000 of pairs of hand-labeled shoes. Now we have some. What is shoe pairing actually? We define shoe pairing as finding in shoe population shoes which are pairs. So this is pretty straightforward. Here we show pairs with the blue line. How to measure if pairing is correct? What can be a good metric for this? So we've come up with a metric called pairing accuracy, which is kinda similar to accuracy used in classification tasks, but not so much. The similar part is that we use the correct answers divided by the whole population, but the difference is in our task of shoe pairing, this is the population size is variable. So you can imagine that pairing small population could be the easier task than the pairing a huge population, which actually is. So we consider two cases: one easy population, which only consists of pairs, and the hard case, which is the general case, which admits the single shoes into the population. So let's consider the number of possible pairings depending in context of population size. So if you have only two shoes, you can pair them in only one way, so number of pairing is 1. But if you have 4 shoes, you can pair them in 3 different ways, so the number of possible pairing is 3. If you would like to know how much pairing there is for the population of 100 shoes, this is a huge number. I cannot even come up with a name, but the population size we are dealing with is more like 1,000, and this number is unimaginable. And for the harder case, those numbers are even scarier. So I know this slide is dense, but what I want you to remember is that the number of possible pairings you have to pick one from is growing exponentially or even faster with the population of shoe population to pair. So you have to always think about not only the pairing accuracy itself, but pairing accuracy on given size of the population, because difficulty of this task is getting higher and higher as the population grows. Okay, so our pairing method is a two-parter actually. Only first part, representation learning, is machine learning based, and the other one is some kind of clustering. So in the first part, representation learning, we learn how to transform shoes from the pixel representation to the points in multidimensional space. And we do it in such a manner that similar shoes ends up in similar place and dissimilar shoes ends up far away in the multidimensional space. What we use is actually a variant of triplet learning, where you present the network with 3 items and use triplet loss in such a way that the network is optimized to bring those two closer and those two apart. The red block here is VGG16 pre-trained on image network, so ImageNet, sorry. So we used transfer learning because our dataset was initially very small, and this yielded a huge accuracy boost. The part 2, clustering, is really straightforward. We pick 2 points in the multidimensional data in multidimensional space, which are the closest together, and if they are closer than a threshold, we yield a pair, and we do this while we can. We also experimented with some more complicated regimes for clustering, but they didn't yield much of a performance boost. What is this threshold? We try to stop pairing at different numbers. We sampled it from the whole spectrum and picked the number of and picked the threshold to meet requirements of the proportion of false negative to false positive according to needs of our part. And the results. So for the easy case, we did 99% for a 1000 of paired shoes. For a harder case where the population was 100 paired and 100 unpaired shoes, we are getting approximately 0.98 pairing accuracy. And some takeaways. If you can, do the transfer learning. This is really beneficial to your solution. If you have multiple images of single item, also use them, because you are giving the network opportunity to train from more data. If you are using metric which is depending on the population size, please pass the population size along with the pairing accuracy or your metric. Don't separate them. And the last one, if you are working with some physical process and it's throttling the request per second, for example, in our case, the conveyor belt cannot process more than 1.5 shoe per second, maybe you should consider saving some money and don't going for a cloud or distributed environment. This is all I got. Thank you for listening.
Thank you very much for the presentation. And we invite the author. Oh, hello.
Hello, can you hear me?
Yes, of course. Hello. We have the first question from the audience, which is, of course, very important, I think. Can you do the same with the socks?
Possibly, yes, but not out of the box, I guess. But I like this question very much.
Do you think it will be more complicated?
If you have enough data set, the same setup should be okay. But photos, there are some angles in this experiment, in this research. For example, because SOC is flat, I guess. It's like only on the surface. So some angles of photos do not make sense for SOCs, but other from that it should be viable.
Yeah, the task is not trivial, as the author of the question mentioned. Yes, especially after washing the socks, yes, many times. That might be problematic. Yes.
Let's maybe not dive into that topic.
Okay. Then one more quick question from me. You mentioned about that shoe labeling app which you created at the beginning, yes, which is of course very important part of that work to prepare a good labeling, yes. Have you considered now, after having lots of data labels at that moment, to maybe switch to some semi-supervised solution to use that what we already have and to propose something which can now continue without, when we have a new data, without additional labeling?
We haven't, to be honest, yet, because the acquiring data is also not free, because our partner have to spend some money to prepare the data acquisition. So this process also requires people and also generates costs. So it's not like we have tons of unlabeled data. Unlabeled data is also pretty scarce.
Mm-hmm. Okay, thank you very much. One more time for the presentation.
Thank you.
Let's quickly continue. Now we are moving to the next presentation of today's session. The title for that presentation is a representation of observation in performance learning for playing arcade fighting games. Let's see the presentations.
Good morning, ladies and gentlemen. My name is Huaiyu Du. It's a great honor and a pleasure to have this opportunity to participate in this event. Today, my presentation's topic is representation of observations in reinforcement learning for playing arcade fighting game. Here is the main content of today's presentation. The game I chose is The King of Fighters 97. which is my favorite arcade game. The controller of the game consists of one joystick and 4 action buttons. The main challenge of playing such a game is mastering the complex command system. As you see, the special move and desperation moves command consists of a sequence of joystick movement and action button presses. Especially, the desperation moves command is pretty long and it needs to consume a power up. In order to train a model, the first thing is to set up a Python game environment. Here we used an arcade game emulator called MAME. In the console, we can manipulate the game via Lua script in a programming way. The hook, which is called after every frame rendered, provides the ability to interact with the game at every time step. An open-source Python lib called MAME Toolkit encapsulates all the Lua script functions into Python classes. Our game environment is built up based on this lib, and it implements the OpenGym env interface, which is a standard in the reinforcement learning field. There are 49 discrete actions in the action space, including all meaningful combinations of the input signal. Here is the reward system we proposed. 1P indicates player 1, which is our reinforcement learning agent. 2P indicates player 2, which is the built-in AI. The first two terms are damage reward and damage penalty. The priority is to win the game, so it's quite natural that if the agent deals damage, it gets a reward. If the opponent deals damage, it gets a penalty. To encourage the agent to perform more combos, the damage, the reward and the penalty are amplified by the combo count. On top of that, we also introduced the two factors gamma 1p and gamma 2p to adjust the agent's behavior. For example, if you want the agent to be more aggressively, you can increase the value of gamma 1p. The next term is distance penalty. G here indicates the distance between the two characters. If the distance exceeds some threshold beta, the agent will get a small penalty. By introducing this term, we want the agent can keep a reasonable distance between the two characters. The next term is the time penalty. At every time steps, the agent will get a small penalty. It's used to encourage the agent to be more active to deal damage and win the game as soon as possible. And the last term is the power consumption penalty. Once a power orb is consumed, the agent will get a medium penalty. If later the desperation move can hit the opponent, the reward will counterweight this penalty. Otherwise, the agent will be punished for wasting a power orb. The observation vector consists of several parts. The first part is the basic information that can be observed from the screen, such as the character's HP, position, status, and so on. And the next part is the character's action code. There are one-hot encoding vectors. And the last part is the agent's input. It's also a one-hot encoding vector. But only having the information from one step is not enough for the agent to make an optimal decision. To preserve the Markov property, we must maintain the observations of character's action code and the agent's input for several steps. By By stacking these one-hot encoding vectors, binary images are formed. These images encode the character's input and the behavioral pattern, and which can be retrieved and recognized by the CNN networks. And the result will be fed to other multi-layer perceptrons with the basic features. The models are trained on a personal computer with a 12-core CPU and an RTX 3060 GPU with 12 environments run in parallel. Our first model, the agent operates the character URI to fight against the kill. And then using transfer learning, we trained another 3 models to fight against the other characters. Here is the result. As you see, all these models achieved a 100% win rate. From the learning curves, you can see that the transfer learning models achieved a similar performance with the one learned from scratch, but they used less time. Okay, it's showtime. Thank you. That's all.
Okay, thank you very much for very interesting presentation. And we see the author. Hello.
Hello. Can you hear me or see me?
Yeah. Yes, we hear you. We have
Hi.
one question from the audience, so I will present that. You probably also see. Do you think we could use the same method to train the network to play in VR?
I mean, yes. I'm not sure yet. I think ISMET has some difficulties because the representation of the game is using a vector, maybe 1000 dimension vector. And in terms of VR, I think the most challenging part is to use some computer vision technology to analyze what you see and how to present the environment. And I think this is the most challenging part. And of course, the environment is way complex than a traditional fighting game. So I'm afraid for now, maybe it's not possible.
Mm-hmm. No, but assuming that we maybe, in some sense, find a way to vectorize the representation from three-dimensional space in virtual environment, would it be possible maybe to put that in some sense to the methodology of observation?
Sorry, can you?
We have just 3 degrees of freedom, yes?
Yes.
Maybe that's assuming the vector of observation, yes, which we have.
Yes.
If we find a way to simplify the representation from 3D space,
yes, way,
to put it to observation.
Yes, I think in that way, if we can find a proper vectorize the observation of the environment, I think it's a feasible way. I think.
Mm-hmm. Okay. No, very interesting presentation. Thank you very much. And now let's skip to our last presentation during our session. The title for the last presentation is AI for You, Modular Framework for AI Application Design. Let's see the presentation.
Hello everyone, my name is Kamil and I'm an employee of the AHP, Leibniz Institute for High Performance Microelectronics. This topic presents concept for a universal modular tool that will enable faster construction of artificial intelligence application. The goal of the concept tool is universal in terms of changing the environment, as well integration of different type of sensor to perform a specific task. Artificial intelligence is very popular in last years. AI is used in many scenarios, from intelligent assistants to advanced real-time vision systems. AI enables devices to make decisions based on data collection from cameras or other sensor. This data is processed and the device can then react based on it. The presented concept of a universal modular tool that enables fast development of artificial intelligence application uses the Sense for You approach, which will improve the construction, process testability, and reliability of applications. The Sense for You idea is based on a fast application building use the modularity of available libraries for non-experts. Currently, systems can be found that provide users with libraries and tools to support the building of robot applications, such as the Robot Operating System or Cube system. Robot Operating System is a meta operating system focused on building robots whose main goal is support user in re-implementing previously written code for robotic research or development. The advantage of ROS is its language universal because software can be written in programming language such as Python, C++, Lisp. ROS is open source software which allows the community to create new solutions. Cube system, on the other hand, is a collection of hardware and programmable components that enable fast prototyping of robots. Cube system combined with the RobLib library allows customization and combination with separate set of libraries. The starting point for the proposed tool in the Space Region project is that was started making prototypes using artificial intelligence. Using Earth scenarios, we create a robot to track and recognize objects. The basic AI application that was developed for the project was to observe the environment, recognize and track people in it. To build the application, we use a platform from the Decorpora called Cubo1. It is a stationary robot in its basic version equipped with 2 video cameras, 2 servos to move, and Arduino board to operate all components, and Raspberry Pi version 3. For the purpose of real-time computer vision, the Raspberry version 3 was replaced by version 4, and additionally an AI accelerator was added. For low computing power devices, functionality to support AI accelerators can be implemented in the proposed concept tool. One such accelerator is, for example, the Interneural Compute Stick tool. Then during the ongoing work in the Space Region project, the idea of a mobile robot emerged. The second prototype is a mobile robot whose task was to detect objects and follow them. Similarly to the stationary robot, the mobile robot was equipped with a Raspberry Pi version 4 and an Interneural Compute Stick 2 accelerator. In addition, it was planned to explore the possibility of easily transferring sample application to more demanding environments. Moving from the Earth solution to a space solution requires the replacement of sensors or actuators to meet the new conditions, but in order not to write application from scratch, this can be done in a modular way. The programming language used to build the application is Python version 3. Python is a high clever programming language, and thanks to its simplicity and universality, it has become an ideal tool for building prototype artificial intelligence systems. When building the mobile platform, it's turned out the code responsible for computer vision could be transferred directly, and only the variables responsible for the resolution or the camera port were modified, while the code responsible for controlling the robot was completely changed. The concept tool present should allow the application to perform its task when the original sensors and actuators are replaced by devices that can survive the new environmental condition. The aim of the proposed tool is to create software that will be a set of dedicated libraries, but the modification introduced in the concept tool will allow the same action to perform on different sensors. The application should use a generic application programming interface to use the features of the devices and adapt to the physical characteristic that this device offer. Replacing one device with another does not change the implementation of the application, although it may change its internal behavior and functions. The API should give the application control over the device and provide information about its properties. An application developer using the concept tool will be able to obtain a list of available functions for a given sensor. When building the tool, it will be necessary to define the communication interface with the user and the parameters that the user will need to enter in order for the tool to work properly. For example, a user building a robot uses built-in DC motors. Using the API functions of the concept tool, for example, the user could call a method to retrieve features for the DC motors. This method would return data to the user containing what parameters the user should enter and the available features for the DC motors. Another functionality of the tool concept is its modularity to support modification. An example is the modification of the side robot by the user. The user replaces the standard DC motors with stepper motors, which introduce a number of changes to the developed main application. However, when using the proposed concept tool, the only modification on the user side would be a possible change in the name of the motors used. The basic functionality would be unchanged for both motors, and the operation of the program after changing the motors would not be affected. Furthermore, after the modification, calling the method to retrieve the features for the stepper motor will result in more available features being displayed because the stepper motor can be rotated about set degrees. The presented concept of the tool is under development and may change during implementation when new problems and changes are discovered in the Space Region project. The proposed tool which allow for expansion with new libraries depending on user needs. The main advantage of the concept tool would be a reliability to environmental changes and the unification of functionality for sensor of the same type would allow fast design modifications. We will also analyze and compare the implemented code for different scenarios in order to find common parts that will eventually be transferred to the proposed tool. A library consisting of several sensors of the same type will be created to test the behavior of the application when it is modified. Furthermore, example application related to artificial intelligence, robotics, and computer vision will be created using the concept tool. In addition, an analysis of the application will be carried out in terms of modifications when scenarios change. The main objective of the proposed concept tool is to simplify the construction of artificial intelligence application. Thank you very much.
Thank you very much. Hello.
Hello.
See the author. Hello.
Can you hear me?
Yes, we hear you. I'm looking for some question. You mentioned about the application, piles of application for that platform, yes, in context of space research, yes. Have you considered other application area, for example, to adapt that platform to some educational purpose, yes, for example, as a platform which can serve as a platform which allows I don't know, children in school also to make some simple form of programming of AI with such a modular platform?
Good question.
Using a robot in sense of educational, purpose, yes? Controlling the robot, creating environment for such a robot.
Yes, but because on this moment is hard. This question is hard because I'm in the process of implementation, and at the moment it is hard to say more because it is a concept, and problems with the application and environment for use this application, it's coming out during the implementation, I think.
Okay. Thank you for your answer. Okay, I'm looking. Do we have any other question? I can't see any other questions. So at that moment, I want to thank you one more time for your presentation. And that was the last presentation during our session. So one more time, I want to thank you to all the presenters for your presentation. We watched 6 very interesting presentations with different topics, different side of application of machine intelligence. All topics was very interesting. It was my great pleasure to be the chair of that session. I hope it was very also interesting for all the people which joined our session to see that presentation. No, as a last information from me, just like I mentioned at the beginning, after we finish the session, the special dedicated breakout rooms will be available. First of all, I would like to ask all the presenter as a first to join that rooms and to be available during a break in that rooms for some possible additional question or some possible meetings with other participants of our conference. So please join that room and be available. Of course, I invite other people who are interested in some topics to join to that rooms also and to not start additional conversation. Maybe that will open some new research perspective for you to continue also with other teams. Maybe some new cooperation will be created. Thank you one more time for that session. So formally, I'm closing our session and I invite you to the break.
Thank you very much, Rafał, and thanks to all the authors for interesting presentations. Like Rafał said, we now have a breakout room open for the authors and other people interested in discussing the papers that were just presented, and we'll be coming back at 11:50 for meditation session. So if you are, I of course encourage you to join us. We'll have a meditation session before the next session of presentations and after the discussion in the breakout rooms. So if you're not interested in joining breakout rooms at the moment, you can have a moment of break. So see you soon at 11:50. Okay, the breakout rooms are now closed, so we are ready to move to the next point in our agenda, which is a meditation session. After that, we'll come back with a little bit of entertainment and the next session with presentations of the paper. So now we can make floor for Gabriela Górska from our institute, and she will, as a master of meditation, she will lead current session. I hope it will be a good break for everyone to clear their minds and prepare for the next session with presentation of papers. Hi, Gabriela, can you hear me?
Hello, yes, perfectly. Can you hear me?
Yes, we hear you, we see you, so the floor is yours.
Thank you very much. So it will be important to hear me for the next 10 minutes. I will conduct a meditation for you so you can relax and Just remember, as we said in the video introduction, you're not glued to your chair in any way, so you can just relax and sit wherever you want. I hope my video is working. I mean, we don't need actually my video, we need my voice, but I see myself frozen a little bit. Okay. So just remember, dear meditators, that you can just go wherever you want for the next couple of minutes or even for the whole meditation. You don't need to sit in front of your laptop. And just for this one little moment, stay in the moment, in the place where you're at. We will try to move our minds a little bit away from thinking about theories, conferences, cyberspace even. So please move yourself in such a way that you'll be comfortable for the next few minutes. And we will do an exercise as the first meditation that is called body scan. So we will go slowly with our focus through our bodies. So if you're ready, you can close your eyes, but you don't have to if you don't want to. Take one deep breath in and breath out. Now I would like to ask you to slowly try to concentrate on your left foot. And move slowly your focus through your leg to your knee, the left knee. While you're still breathing and experiencing your body the way it is. Now you can switch your focus to your left hip. Now to your right foot. Just remember that whatever happens during this exercise in your mind just happens in your mind. They are not real events. They just happen in your mind. And if you feel pain anywhere, it's okay. Your body is allowed to produce pain as well. Try to focus your attention on your right knee and in general your right leg up to the right hip. If you're sitting, try to focus on the parts of your body that allow you to sit or connect you with the thing you're sitting on. For this moment, you can focus on your bottom, on your belly, on your crotch, on the hips, both sides, and then slowly move your attention up to your digesting system. Maybe there's some noises that you can hear. So also we don't need to judge them. We can just come and go. Maybe you can feel your torso. Your ribs, your lungs, how they spread, how your body is working when you're breathing. Maybe you can feel your back. On both sides. Your arms. Please feel free to move your attention to the right arm, right elbow, and the right hand, while still breathing. And slowly move your attention to the left arm, elbow, and hand, including all the fingers. You can slowly move your attention to your neck, your throat. Maybe you can feel the air passing in and out. Your nose. Maybe you can feel the temperature of the air. Your face, ears, your forehead, and your head in general. As we're focused now on our heads, and trying to feel them instead of thinking about them, please take 2 more deep breaths in and out. And if you had throughout this experience your eyes opened, you can closed, you can open them right now. Slowly. Just see where you are. The real world. Just see the space around you, maybe what's outside the window, who's around you. And for now, we will finish this experience, but there's more coming. So let me produce a sound as a symbol of finishing this one exercise. Thank you very much.
Thank you. I hope that you all feel just relaxed as we do here in the studio. We have a guest here with us. It's Dr. Wiesław Kopeć, co-chair of our conference. We we are glad that you are here today.
I'm glad too, and I would like to cordially welcome everyone on the second day of our conference. And now we are.
Yeah, now we have time for a little bit of entertainment. We have a quiz prepared for you. It will be a quiz regarding a bit of history of information technology, because it doesn't matter if you're a specialist in artificial intelligence or in human technology interaction, you should know your roots.
Yeah, the fundamentals of our discipline. Yeah.
Yeah. So we have the quiz for you. We wait for the link to appear so you can join. Will we have a link on the screen?
Yeah. Just a sec.
Yeah, I think we have some little bit of problems. All right. So, in order to participate in the quiz, you have to go to menti.com, and there you will be asked to use a code. And when you enter the code, you will be taken to our quiz. So we can wait a bit, maybe for more people to participate, and we will be starting in a moment. Okay, yeah, the crocodile. Oh, right, the crocodile, the fish. More people.
Frog.
Unicorn. We have a unicorn also. Okay, I think that we can start.
Yeah, why not?
All right. So you'll see the question, and in order to get the highest number of points, you need to act quickly. So the question is, who developed Python programming language? We have a bit of time for. Do you know the answer?
No, of course I know.
Okay.
Cool.
We have to wait a moment to give time to everyone to answer, and we'll see. All right.
So, what's the wisdom of the crowd? Yeah, definitely.
That's good. So Guido van Rossum was the creator of a Python language, widely used today, very often for machine learning.
Yeah,
very popular for this.
Okay, data analysis.
Yeah, of course. Okay, so we can move to the next question.
Tom. Oh, this is a tricky question.
Yeah, what keyboard layout was first? But you only have two answers, so
it's 50-50.
50-50. Probably a bit easier, maybe.
And 10 more seconds. Great. So, what do you think?
Azerte. No, I was wrong. I was wrong.
All right.
Yeah, many other. Actually, before QWERTY, there were many other layouts. Okay, so we can move to the next question. Wiesław, can you read?
What was the name of the first commercially available microprocessor? Tom. I suppose I know the answer.
Okay.
It also might be a bit challenging, and once again we will check the power of wisdom of the crowd. So crowdsourcing,
that's true
in practical application. Yep, that's great.
All right.
The first Intel microprocessor. Yep. And another question in a row.
The last one was definitely easier for our age group. Let's see now. Okay, is this coded correctly? you have a snippet of HTML. Is it correct according to the rules?
It's a bit tricky, but
yeah, it's not that easy.
Because of the small characters. It's another challenge.
Another challenge.
You know, yeah.
So if you watch the question, take your glasses and see the details.
Yes.
No, yes, that was the correct answer.
That was on the opening tag. Alrighty, yeah. So the next question in a row. What is Charles Babbage known for?
Yeah.
Another fundamental from a blast from the past.
Yeah. So the answers are: he originated the concept of digital programmable computer. He was the first person to use the word computer. He built the first computer in 1831, and the last one, Wiesław?
He wrote the first computer program.
All right.
So it's another a bit tricky question, but we will see what's the power of wisdom of the crowd.
Even we are too young for that one. 1831.
So yeah, the first one was correct.
Yeah. So he originated the concept. Of course, it was too early to build the computer then.
Yeah.
But
so
the idea was there. Okay, we can move on. Okay, we can see the leaderboard. Yes, Przemo, which is a strawberry.
Strawberry,
the fastest. And with 4,500 points. And Gabriela and Wolfmeister are on the third and second place. Okay, we can
now move to the next question. So it was like in the middle scoreboard. Which one of these is regarded as a first computer virus? Yeah, okay. It's another historical moment.
Rabbit, Creeper, Code Red, or First Trojan.
Perfect names. Three, two, one, go.
And go.
Time's up. And yeah,
Creeper.
The Creeper program, and it was really hard question, directly from the history of applicable part of information technology. Alrighty, so the next question.
You could get misled because Creeper is a creature from Minecraft currently. So.
Who invented universal Turing machine? That's the tricky question.
Was it Turing?
I don't know.
Was it Ada Lovelace? Was it Edgar Code?
Maybe Claude Shannon. Each of those figures are really important persons from the history of and fundamentals of information technology and computer science. And time's up. Let's see. Yep.
Yeah.
So this one, it was straightforward.
But you know, tricky because it was straightforward.
But sometimes it may be more tricky. We'll see. All right. So what's the next question?
8.
How is the Morse code for SOS written out? So very
useful,
practical knowledge and question.
Definitely.
So,
if someone is quick enough, can enter it in the Morse code translators online.
Yep, it's possible, it's viable.
Okay, but time's up, and the right answer is...
Yep, the last one.
The last one, okay. So in general, people, for the most question, most answers were...
Yeah, so the wisdom of the crowd is working.
Definitely.
Inevitably, yeah. So another question. What does RAM stands for? you know, at the first place, I wondered to, I would like to say the whole name for this acronym, but you know.
Yeah, it would be too easy.
Yeah, it would be too easy. So, fundamental part of every contemporary computer system, including mobile phones, smartwatches. Yep. And yeah, the third answer is correct. And again, the majority of our
knew the right answer.
Respondents.
Yeah, it was random access memory. Okay, so we are at the question 10 from 15. What language use these signs for an assignment operator? Okay. So we have some older languages, I might say, like Algo, Pascal, C++, C#, Python, or HTML.
And we will see in a minute.
If we have programmers here. Yeah, we do.
Yes. I think that elimination is the best
maybe
strategy in this case.
Have you ever used Pascal?
Of course, it's the best language for trying to learn algorithms and data structures.
I used it in high school. And I liked it. I liked it very much, I must say. Okay, so we have a leaderboard again. The Przemo lost his lead to Jan Klimaszewski, but they are very close, and I think everything can change between. We have 5 questions left.
Yeah. So the final stage of our competition.
Yeah.
What does this stand for?
Okay.
Without any context. Alrighty.
Morse code. Hello.
It's almost like Latin sentence with all capital letters. Cool.
Winter. Hello.
We will see.
Yeah, you should. I think that in order to answer this question, you should know not only binary but also ASCII codes.
Or just
hello.
Count the bytes. So 5 bytes each for one letter. Great.
Yeah. So the first thing you do in every language when you learn programming is hello world. So
hello world, and you may count just the letters because it's like 5 letters in a row. Alrighty. Okay. So what does 33 stand for in ASCII code?
Yeah. So we are back. So
another lookup in the internet.
Quick lookup.
Sneak peek for the answer.
No. We assume that every scientist knows ASCII code
by heart.
Of course.
Sure.
Very easy question.
Very easy. Three, 2, 1, and time's up. And it was tricky.
No,
really
it was
tricky.
a tricky one. So yeah, there is a bit of place for improvement.
Yeah, and it's definitely it's a challenge.
Yeah. So remember, learn your ASCII codes.
What is this? Great question.
What is this?
What is this? A quantum computer, the smallest computer chip.
Telescope or nano-accurate microscope. I hope that we have the image right.
Maybe there's a little mismatch. Yeah. We will see. What was the intention for this question?
I would add other answer. It's a pint of beer.
Perhaps. Yeah, it's a quantum computer. Example of course.
Yeah.
Great. And the last question we will see.
Yeah.
In a moment. So, what was the word computer first used? It's more social context.
1822, 1613, 1854, and
1456.
All right.
Yeah. Tum tum tum. And we will see in a minute, because it's also a bit tricky question.
Yeah.
It's all about the computation. So time's up. Nope.
Easier that you might suspect. Earlier that you might suspect, but it was not. The question was not easy because of that.
Alrighty. So what's the final score?
Yeah.
And
is it Przemo or is it Jan Klimaszewski?
Dun, dun.
They are very close, but the winner is Jan Klimaszewski with 8,242 points. Yeah, we'll have a small set of gifts for the winner. From what I know, Jan is from Warsaw University of Technology, so it will be. I hope it will be easy to arrange. And it's great that he is here because he is also a chair of upcoming session.
That's great.
Presentation sessions together with Jakub Morzaren.
So maybe instead of this model of quantum computer, we may just turn it into your proposition.
Yeah.
Yeah.
Okay, so the game is over. Thank you. It was great having you here for the game. I might add that in the next days we'll also have games with different topics. So yeah, and I encourage you to be here and to participate because the prizes are really great. Prizes are really great, and so we can now move on to the session. This is one of the new things in our conference, one of the special invited sessions, and we are really great that this idea came out, and scientists from Warsaw University Technology decided to contact us with the concept of the sessions. Yes, it's great. The session here will be about collaborative robotics. And speaking of robotics, I have a question for you, a quiz for you.
Oh, a special quiz for me.
Yes, special quiz for you. How do you know how do robots say goodbye?
Oh, I have no idea.
It's quite easy. They use binary.
Slap.
We had a binary in the quiz, so everything comes together, I think, very well.
I think that we should, have a bit of distance for ourselves because,
definitely,
on the regular basis we do very serious science, but from time to time it's a room also for some jokes. Even not the best ones.
Definitely the very, very bad ones.
Yeah, all right.
Yeah, but this also became kind of a tradition for the conference, and I think that now I'm obligated to make this kind of jokes, and I hope that someone laughed.
Yeah, I hope that this intermezzo was very interesting for you too, and entertaining a bit. So you had a time for grab a cup of coffee and prepare for the next really interesting session on the vital, one of the most important challenge in contemporary computer science. I mean, it's more transdisciplinary problem that just things related to computational matters. So because there is not only robotics but also human-robot interaction. So there is a lot of interesting stuff for our audience and our conference. So thank you again. Many thanks for Jakub Morzaren for proposing this session, and we hope that everyone will enjoy this marvelous session.
Yeah, I think we can start. Do we have Jan Klimaszewski and Jakub Morzaren with us?
Yes, hello.
All right, great. Okay, so we can start the session. The floor is yours.
Okay, thank you for this great introduction and fun games. My name is Jan Klimaszewski and I'm from Institute of Automatic Control and Robotics, Faculty of Mechatronics and Warsaw University of Technology. And I will, with my colleague Jakub Mrzaren, I will co-chair this session. I'm pleased to welcome everyone gathered for the Advances in Collaborative Robotics special session. In a moment, we will hear the pre-recorded video presentations prepared by the authors. There will be a few minutes for live question and answers after each presentation. And to avoid problems with timing, we encourage conference participants to ask questions and make comments in the chat. So I can read them out after the video presentation. And one more technical detail for presenters. I would like you to remind that you have to click join the audio button before you can be muted and unmuted on demand by the technical team. And please be ready to switch on your cameras and unmute yourselves for the Q&As after the presentations. After this short introduction, I think we are ready for the first presentation, and we will hear about NRRX, Recurrent Neural Network Model of the Graphene-based electronic skin sensor with hysteretic behavior by Jakub Mrzaren.
Welcome everyone. During my presentation, I want to talk about recent research on electronic skin technology carried at the Institute of Automatic Control and Robotics at the Warsaw University of Technology. I will present the recurrent neural network model of the graphene-based electronic skin sensors with hysteretic behavior. This research is a part of the larger project aimed at developing electronic skin and technologies allowing robots to obtain new sensing abilities. Our group has the following motto: it's not easy to give a robot a sense of touch, but we keep on trying. First, start with the basics. Human or animal skin is the thin layer of tissue forming a natural outer covering of the body. It is a protective barrier against mechanical, thermal, and physical injury and hazardous substances. It is a sensory organ that senses touch, temperature, strain, and moisture. It should be emphasized that touch is one of the most natural ways of human interaction with the environment. Therefore, we developed the technology of the electronic skin, so-called e-skin. This interface mimics a biological tissue that allows for increased safety in human-machine cooperation and the agility of robotic manipulators or soft robots. The e-skin technology covers different areas that we can see in the following figure. For example, it is being developed in medicine for smart health care or prosthetics. Such technology should be large-scale, flexible, and characterized by high resolution and sensibility. Current strain gauge designs include resistive, capacitive architectures of piezoelectric materials. However, such technologies are poorly scalable and have low sensitivity. Electronic skin requires induced sensitivity in a specific range of human perception of induced force. Moreover, to attain spatial sensing ability comparable with natural skin, they should be integrated into an array form whose single device are as small as biosensory cells. They can be then placed on a flexible or stretchable material. Graphene is a two-dimensional allotrope of carbon that can be a prospective candidate for e-skin sensor technology. It has strong mechanical properties and flexibility, including recovery from mechanical stress. Additionally, its two-dimensional nature allows the formation of continuous films with high force sensitivity, so the graphene sensors can be put on the cloth or some soft material. The e-skin graphene sensors manifest hysteretic behavior. However, the visible effect of hysteresis on its modeling accuracy has not yet been discussed. Hysteresis is the dependence of the state of a system on the state's history, and we can find this phenomenon in many science fields. Non-hysteretic models capture the general features of many systems with hysteresis that can be classified as algebraic, differential, or integral models. One of the promising solutions is to use recurrent neural networks to model the systems with hysteretic behavior, mostly because of their ability to approximate nonlinear dependencies and, of course, the recurrent neural network memory properties. The presented research aims to propose a novel e-skin graphene sensor modeling method using the nonlinear autoregressive exogenous recurrent neural network that can describe the hysteretic behavior of the sensor. In our research, a matrix with 16 rows and 32 columns was used with the size of a single sensor, approximately 5 by 5 mm. The electronic skin controller measured the readouts for each sensor and transmitted the position and touch force exerted on the active surface to the database. Then we could process the data and visualize the touch results as a color-coded image. The measurement acquisition setup presented in the figure comprised the FANUC LR-Mate 200 IC manipulator, the on-robot HEX-E 6-axis force and torque measuring device, and the electronic skin with a controller. Data from electronic skin sensors and the reference HEX sensor were acquired during the calibration procedure. Data acquisition was divided into two phases. First was the loading phase, presented as the blue line in the figure, when the force exerted by manipulator on a sensor increased. And the second phase, presented in the red line in the figure, was the unloading phase when the force decreased. The sensor readouts are characterized by visible hysteresis and significant differences in parameters of different sensors for a similar acquisition procedure. In the figure, we see readouts from 4 sensors. Therefore, the purpose of our research was to propose a general mathematical model able to approximate readouts from the set of different sensors. To model the e-skin graphene sensor, I have used a nonlinear autoregressive exogenous model in the form of the recurrent artificial neural network. It has one nonlinear layer with different number of neurons, one linear layer with one neuron, output feedback, and the input signal delay lines. The input signal to the network is the sensor readout, and the output signal is the measured force. As a performance function during neural network training, I have used the mean squared error. Weight selection was based on the Levenberg-Marquardt algorithm and a variable matrix method, and weights were updated in batch mode. The early stop method was used during training by segmentation of the dataset into training, testing, and validation subsets. Weights and biases were initialized using the Nguyen-Widrow initialization procedure. The values of the sensor readouts and HEX readouts were normalized to the range between 0 and 1 to avoid neuron saturation. The quality of the neural model was evaluated based on the mean squared error, and the goodness of fit between the estimated data and the reference data was calculated as root mean square error. The two types of neuron transfer functions in the nonlinear hidden layer were used. They were either a hyperbolic tangent sigmoid transfer function or a symmetric saturating linear transfer function. The table presented in this slide covers quality indexes of the recurrent neural network models for loading and unloading phases. The red color indicates the quality index values after training. It can be seen that the model's accuracy improved significantly after training. The values are independent of the type of the transfer function, but for the saturating linear transfer function, there were fewer training iterations. In the next figure, I'll show results for the recurrent neural network with only one neuron in the nonlinear layer. On the left-hand side, we see almost the same data from the sensor and the recurrent neural network model. On the right-hand side, there are residuals shown for the loading and unloading phases. It proves the high accuracy of the model. So now, it's a time for short discussion. The obtained results indicate that, first, quality indexes are similar for the loading and unloading phases, thus properly modeling the hysteretic behavior of the sensor. Second, The estimation errors after training do not depend significantly on the number of neurons in the hidden layer, even only if one neuron is used. And third, the number of iteration epochs is few times slower in case of symmetric saturating linear transfer function, describing neurons in the hidden layer. There were between 14 to 21 epochs, compared with the hyperbolic tangent sigmoid transfer function used in the hidden layer. There were between 68 to 187 epochs. So let's summarize. In the presentation, I have described the possibility of touch force estimation of the electronic skin graphene force sensors with hysteretic behavior using recurrent neural networks. The presented method provides a simple alternative to electronic skin graphene force sensors models known in the literature. Further research should be done to extend the developed model to the sensor matrix, such as the layered deep neural networks for electronic skin calibration and data compression. It makes us closer to reaching our goal and equipping machines with the touch sense similar to animals or humans. So finally, I would like to thank a few people. First, our electronic skin research group from the Faculty of Mechatronics of Warsaw University of Technology. For very nice drawings, I would like to thank the illustrator Marcin Ponomarev, who is a very talented person and creates very nice comics and graphics for the computer games. And for the presentation, I would like to thank Patrycja Jakubczyk for the inspiration in preparing the scenario for the presentation. Finally, there are some publications that I would like to recommend for further reading. Thank you for your attention.
Thank you very much, Jakub, for your presentation. I would like to ask you to switch on your camera. You can shortly present yourself and we can start the Q&As.
Sure. So, quickly speaking, I'm also from the same department as you, Janek, so from the Faculty of Mechatronics from Warsaw University of Technology. And I will be co-chairing this session for the next few papers, but first I would like to answer your question, if you have some, about my research that I have done on neural networks.
So I'm looking into the chat and see no questions for now, but we can wait a few seconds. Or someone can voice out their question also. If there will be no question, I have one prepared for this occasion. Or if there will be question, I still will have one question. If there will be time for this. Okay, so maybe I will start. Jakub, I have one question, because when we train neural networks, the data set used for training usually is divided into 3 sets: training, validation, and test sets. And you've presented some error results of your modeling with neural networks, and those are the results for which data set of the before mentioned by me?
Yeah, thanks for this question. The thing is that maybe I should indicate it in the presentation, but frankly speaking, I haven't. And these results are in fact for the data that I have used for the training. And but in fact, both data sets and for the training and testing gave similar results. The testing were slightly worse, as we can expect from the neural network training. That, you know, this is the data that you would like to generalize the results for. But frankly speaking, you know, the technology that I presented here proves, in fact, that we obtain a very, very good results even with very, very simple designs of the recurrent neural network. So therefore, it could be somehow, let's say, used for different sensors of the type. But like talking about the results, in fact, this table is only for the training dataset.
Okay, thank you very much. Are there any further questions? Okay. If there aren't any other questions, I think we can finish the questions to these presentations. Thank you, Jakub, for all the explanations. And I think we can count on a wider discussion in breakout rooms. And now we can proceed with the next presentation.
Okay, Janek, I think the next presentation, I think I will take over chairing now, okay? Because
yes.
the thing is that it's your paper, so probably I should now ask some questions, and I just should introduce you.
Okay, so thank you for co-chairing.
Yeah, so that's the thing. So the next paper will be by Jan Klimaszewski and Przemysław Białrucki, and the paper will be on the proximity estimation for electronic skin placed on collaborative robot conductive case.
Hello, my name is Przemysław Białrucki. I'm from Warsaw University of Technology. Me and Jan Klimaszewski are exploring the possibilities of using electronic skin to improve the safety of work with robots. In this presentation, I will show the results of our research of proximity estimation for electronic skin placed on robot conductive case. In recent years, an increasing number of areas can be observed that enable human-robot collaboration in the same workspace. The demand for such robotic application is emerging in industry, education, medical services, security. Cobots have become an essential component of Industry 4.0. One of the key issues in human-machine collaboration is human safety. In order to ensure that the effects of collision with humans are minimized, the construction used in cobots can be lightweight and compliant, and there is a reduction in power and strength of such machines. Another approach is equip cobots with electric skin, which will allow to detection of the human approaching the robot's casing and stop robot before collision. The electronic skin works on the principle of measuring the capacitance of open capacitor. When object is close to open capacitor, the relative electrical permeability in the area of the sensor changes. The electronic system receives these changes and based on them makes it possible to infer the detection of object in its vicinity. This paper presents analysis of the results of estimating the proximity of human to robot with electronic skin placed on its surface. The main components of the hardware setup are the electronic skin, numbered 2 on the picture, together with the measuring controller, FANUC industrial robot, and the PC. The experiment consisted in approaching open human hand to the surface of the electronic skin, which was placed on the robot. The result of the measurement is the number of periods of the signal generated in the electronics measurement system measured over a fixed time interval. Changes in this number indicate a change in the relative electrical permeability in the area of sensor, which makes it possible to infer the detection of object in this vicinity. During measurement, the constant time interval during which the periods of the generated signal are counted was set to the default value around 700 microseconds. Electronic skin proximity response with the measurement system configured by default is small and relatively difficult to distinguish from measurement noise. Such a result doesn't allow to estimation of the proximity distance, but it's sufficient to detect presence of hand in the vicinity of electronic skin. In order to improve the quality of detection and allow the estimation of the proximity distance of the object, it was necessary to change the response of the system in relation to the noise present. In order to improve the quality of the circuit's response, the fixed time interval in which the periods of the signal generated by the electronic circuit are counted was increased. This was implemented by modifying the microcontroller's internal timer settings. The effects of increasing the value of time periods from around 700 microseconds to around 3 milliseconds. After the modifications were made, the experiment was repeated by bringing the hand close to electronic skin placed on the robot. Figures show example result measurement system. As a result of modification, a more evident response of the electronic skin placed on the robot to the proximity of human hand was obtained. The signal to noise was almost to 200. This represents a much better result than the initial performance. The use of electronic skin estimating proximity on a capacitive basis when placed in close proximity conductors pose problem. These are related to the occurrence of much higher capacitance of the open capacitor resulting from the presence of conductors in the sensor working area than from changes in capacitance resulting from the proximity of objects. This problem is very relevant given the target use of electronic skin as assistive device for a safe robot-human interaction. The housing of such robot is often made of conductive materials. In the manuscript, in order to minimize the problem at hand, the time interval during which the signal periods generated by the electronic system are counted was increased. This improved the response of the system and increased the signal to noise ratio of the measurement system. The negative cost of obtaining such a result is increased response time of the robotic system. Future work on this topic may allow a more precise and robust estimation of the proximity distance of human to electronic skin.
Great, thank you very much. And now I would like to open the discussion. So if you have any questions regarding the topic just presented, please write them in the chat. I hope you have at least one. But if not, I have some. So okay, if you still need some time for writing, you can write them down. I will read them. And I have two questions. So the question is that as far as I understand from your paper and your presentation, the approximate distance of the human hand to the robot that can be measured or detected is like 2 centimeters, 20 millimeter. So it's a very small one. And is it possible to extend this value to, for example, like 10 centimeters or more?
Okay, thank you for the question. I think I can answer that. we started the research with the proximity of human detection for about quite a while ago, and when we achieved results when the electronic skin is not placed on conductive material for about 50 millimeters, we can detect human presence in the vicinity of the electronic skin. And but as stated in this presentation, we would like to place the electronic skin on the conductive case of cobot, or in general case some machine. And with the approach we chosen for proximity estimation, I mean the open conductor, and measuring the response of this open conductor for some signal, we had problems of detecting this proximity of human, placing the electronic skin on conductive case, and in that case we got a response from a few millimeters to maybe 20. I think my colleague writing this paper can say exactly what the distance was of bringing the hand close to the machine.
10 millimeters.
Okay, thank you. So it was the hand proximity detection was about 10 millimeters, but I think it is more than enough to stop the machine and to prevent the collision for low speed, maybe cobot operation. Okay, so we tried to develop a fast or very fast system that reacts in terms of micro or milliseconds, as opposed to, for example, visual systems, vision-based systems that act in the terms of 200 or more milliseconds to detect the human proximity, or even more.
Okay, thank you very much for this answer. I will ask another one during the one-on-one sessions at the end, but so let's maybe, if you have still audience, please, just one question, it would be great, because it means that you are here with us. But if there are no questions, okay, so let's go to the third one, the third presentation, and the third presentation will be presented, prepared by Anna Ostaszewska-Liżewska and Jan Klimaszewski, and the paper is on finite element method based toolchain for simulation of proximity estimation using electronic skin. So please start the presentation.
Hi, I'm Anna Ostaszewska-Liżewska, and together with John Klimaszewski, I would like to tell you a few words about finite element method-based toolchain for simulation of proximity estimation using electronic skin. Well, we are witnessing a real revolution right now, because in earlier times, robots were reserved only for factories and skilled professionals who used to work there, but currently robots have become present in public space, taking over the duties of caregivers, teachers, diagnosticians, and so on. So robots are currently interacting with humans who are not really qualified or even used to that. This situation requires the use of all safety measures to avoid dangerous situations and events. Therefore, work is underway on modern sensors that will meet new challenges. One such sensor is the electronic skin, which was initially intended to mimic the capabilities of a biological organ, but currently broader possibilities for detecting other physical phenomena are being used. We are working on such a solution at the Faculty of Mechatronics of the Warsaw University of Technology. The robotic skin we are working on consists of 2 layers of flexible foil. One has comp electrodes made of conductive material, and in the other there are resistive touch fields that are made based on graphene. The measurement signal here is the resistance of the variable touch fields in relation to the touch pressure is measured, and that's how the touch is estimated. The measure approximation to measure only the approximation, we need just the conductive layer, and it acts as one of the plates of an open capacitor, because the second plate then is a copper reference plate. When there is an object nearby with a different permittivity than the surrounding air, the capacity of this setup changes, and this change is measured using a custom electronics driver based on a rectangular signal generator. For the purpose of modeling validation, a simplified model was proposed, which was built of 2 plates placed on a plane. The plates, together with the surrounding air, act as an open capacitor, in fact. The time, cost, and the amount of work required to produce and test successive e-skin prototypes is really significant. So, therefore, we set ourselves the goal of developing a way to test e-skins without using a physical prototype. We decided to use finite element method, which is not new. The roots date back to the early 60s, and it was developed for solving differential equations numerically, and those equations were defined on meshes of data points. And the idea of mesh is to split the computational domain into a number of simple geometric elements, and over each element the solution function is approximated, and then, finally, the global solution is obtained by combining those individual solutions. FEM is thought to be the most flexible method right now, and it is really broadly used everywhere, especially when the geometries are irregular and when we've got to deal with the steep gradients. The toolchain we have developed consists of NetGen, which is an automatic 3D tetrahedral mesh generator, with Elmer FEM for finite element computation, and here we used some special module for calculating the electrostatic potential in linear dielectric material, and ParaView for data visualization, and last but not least Octave, which is a high-level programming language, and we use that for controlling all the process. Data flow between applications was carried out using text files, and thanks to this solution we were able to validate the results of each stage of modeling, and we were able to do some batch processing. The automation of the calculation was carried by Octave, as I said, as I told you, and well, although each of those programs could be used in Windows, in fact, they have been optimized for Linux, and that's how we use that. And which is the most important here, all the applications were 100% free. The numerical model reflected the conducted experiment, in which a rectangular container filled with water was gradually approached to two plates of an open capacitor. The range distances varied from 1 mm up to 50 mm, and in finite element method model, in addition to the capacitor plates and the water container, the surrounding air had to be taken into account. So this is the green ball in the right picture, and you can also see the distribution of the magnetic potential in space there. Here are the results we obtained. The blue stars in the graph show the simulation results, and the red triangles show the results of the approach measurements. The measurement results are in line with the simulation results. Those small differences can be explained by the uncertainty of measurement. And to sum up, the presented method of numerical modeling enables faster acquisition of knowledge and lower material consumption. The toolchain is all open source, which enables code validation and code modification in case any newly developed material with new physical properties became available. As all programs are free, there is no cost for software license, which is important not only during optimization, but also in the case of commercialization of research results. As there are 4 different applications used, it is possible to perform parallel data processing, which makes workflow optimization possible. Commercial solutions do not offer such possibilities, so it is really worth to copy our workflow. And if you do, feel free to cite us. Thank you.
Great. Thank you very much for the presentation. And I'm opening now the question answer session. So if you have any questions concerning this presented paper and presented results, please write them down.
And my advice is don't make a video at night with your presentation, because otherwise you will sound like that.
Great. I mean, not great, but like it wasn't that. It was quite nice. Like slow. Good mood.
Like
I can say
ASMR.
But, yeah, but like the question. I have a question. Because you propose some workflow which is free, nice, working, but as far as I know about the finite elements method, there is one thing very important here, which is the time consumption. Especially, the algorithms really require the a lot of calculations. And
yeah, if you've got a lot of memory and calls,
if I can finish.
Yeah. Sorry.
Yeah, thanks. So the thing is that I really need the information how it will, for example, like spread when we are talking about the hundreds or thousands of such sensors. Because then we are, because now you it's quite interesting. You showed the example of 2 of them at the picture, and what about when we talk about the hundreds or thousands of sensors and how we model it, and is it possible to then like consider like that we place these elements on the soft 3D shape? then probably the problem will be much more time consuming and require a lot of computational time. So my question is how to make it maybe quicker and easier.
You can do some computation in parallel on several cores, on several computers, on a farm of computers. You can simplify the geometry and just calculate for a part of it if it repeats. There are ways to do that. I don't think it would be any problem for Elmer. Elmer wouldn't be a problem here if you've got thousands of those sensors, because they've got really really simple geometry, and in fact you use just only one module, one solver, which is doesn't have to pass the data to the other module. That would be the problem with parallel computation. But no, I don't expect any problems if you've got more of those sensors to model.
Okay, great. Thanks for the answer. That was the answer. And thanks for the presentation. It was very nice. And now I would like to invite another person, Monika Różańska-Walczuk, that will present another paper, and now it will be about the collaborative robotics and safety and ethical considerations of this technology. So the floor is yours.
My name is Monika Różańska-Walczuk, and I represent the research group from the Institute of Automatic Control and Robotics at Warsaw University of Technology. During my short lecture, I would like to represent collaborative robotics, safety and ethical considerations, the issues which are one of my main field of research interests. For several years, there has been a growing trend related to expectations towards robotics and robots. This relates to the evolving and expanding definition of robotics, which includes the development, creation, and use of robots in everyday life. Robots cooperating safely in one space with people. This is made possible by the intuitive collaboration interfaces they come with. In the introduction to the presentation, I should quote two important definitions that relate to the content of my speech. First of all, collaboration, the action of working with someone to produce or create something. And trust, a psychological state containing the intention to accept vulnerability based on positive expectations of the intentions or behavior of another. So we should ask the question, how to properly design and program robots to collaborate with humans abiding ethical rules. My work aims to present the most important challenges collaborative robots are facing with, in due to necessity, their reliability work, responsible tasks, as well as a closer contact with people. Simultaneously considering ethical standards in robotics without which it will be complicated to gain universal trust and acceptance among the general public. Unlike traditional industrial robots, collaborative robots are designed to work closely with people. Due to the lack of need to use fencing and separate safe zones, cobots are also a good solution in the case of a small amount of available space. Collaborative robots are used in particular in those areas where there is no place to install classic safety systems for robots. Cobots are mobile. They can be relatively easily moved to a new task in another part of the plant, and they are also easy to program. In conclusion, industrial robots are proper for large companies. Smaller companies can more benefit from cobots. When talking about cobots, which we talk about primarily in the context of direct cooperation with a human, and more precisely, safe cooperation, the issue of safety standards should be mentioned. Robot manufacturers set new safety standards that allow to unprotected collaboration. Standards are guidelines relating to the method of project preparation, use, or performance of materials, products, processes, services, systems, or persons. Their task is to standardize information and regulations. Globally harmonized standards help meet market demands, lower costs by standardizing designs, and allow products to be global. They can also provide risk management assistance by helping to limit liability for products. The ISO 15066 standard is the first focusing on cooperation between humans and collaborative robots. It contains detailed guidelines and guidance on how to conduct a risk analysis for collaborative robot applications. The technical specification provides recommendations for collaborative applications where humans and robotic systems work in the same workspace. This is extremely important for the speed and strength parameters of the robot. ISO 15066 distinguishes 4 types of collaborative operation methods aimed at minimizing the risk. The common feature of all these robots is their safe contact with humans. The presence of a robot forces the improvement of order, work organization, etc. Moreover, the mentioned growth of interest in robotics concerns establishing contact with people outside the industrial plant as well. That means robots evoke emotions and build relationships with the user. Ethical standards are a big step forward for people to trust new technologies. Trust leads to acceptance and then to collaboration. Based on research conducted with a team of psychologists, it was confirmed that positive or negative attitude towards robot can be manifested through emotions, evaluations, and reactions, and these have an impact on human well-being. These potential ethical threats are recognized as having a stronger and deeper impact than physical threats. So it is important to consider various ethical harms and countermeasures. Referring to the conclusions of these studies, special attention should be paid to the standard which was published in 2016. The British Standards Institution has published the world's first ethical standard for design, manufacture, sale, and use of social robots. This standard considers ethical issues in social, application, commercial, and environmental terms. Examples of ethical risks and related ethical risks and mitigation measures are presented in the form of a table. Helpful comments are also included with examples of how mitigation and reduction of negative impacts can be verified. Faced ethical dilemmas in the robotics, likewise the AI's matter should be considered. The matter refers to the role of AIs behave in society, example computer programs capable of making decisions for approving home loans. Robots are becoming increasingly involved in our daily lives. So let's summarize. First, the article presents the most important issues related to the development of robotics, how important it is to face the challenges by collaborative, social robots, AMR, and due to their close contact to human. So, safety standards play an important role in defining the baseline for best practices in robotic safety, hazard analysis, project planning, design, system requirement specification, system verification and validation, and quality assurance. And finally, it is very important because robots are becoming increasingly involved in our lives. Artificial intelligence and robotics raise ethical questions. There are extensively discussed certain roles that ethics plays in prosperity of humanity. In conclusion, I would like to ask for a reflection on consideration about an issue that I suppose we will have to face in the near future. Could be robot ethics a possible alternative to robot rights? Thank you for your attention.
Great. Thank you, Monica. So I'm opening the question and answer session part. And if there is any questions to Monica, please ask them in the chat. So maybe we can start the short discussion now, and then, yeah. Okay, so I see the comment from Grzegorz that there is a new threat, namely low trust in science in general. And what do you think about it? So I think this is the question to Monica, and maybe also an open question to all audience.
So hello. I'm Monika Różańska-Walczuk from the Institute of Automatic Control and Robotics at the Warsaw University of Technology. I have to look one more time for the question. Low trust in science. Do you mean? Do you think about? I'm not sure. Do you think about the Uncanny Valley? You mean about this the Uncanny Valley about this low trust in science? I'm not sure if I.
Maybe I can try to say it in other words. People in general have a very low trust in science nowadays. So this is a new threat, and the question is probably will it like slow down the development, for example, and can it endanger trust in technology and robots at all?
I'm not sure. Yes, I see. For example, I see it during my projects with students when we talk about helping and collaborating using robots in our daily life. And I see that after pandemic time, that they are not interested using robots in everyday life as it was previously, even 2 years ago, 3 years ago. But I'm not sure. People are using all the time, and robots are very popular in many. Looking in our lives, they are very popular in restaurants, in some factories or other workspaces. So I'm not sure if robots, or even we can say they are very popular now in medical spaces. Yes. Even hospitals are really interested in using robots during the surgeries or something. I'm not really sure that the robots are in danger or some science is in danger. I'm not. I don't think it's a problem. I think.
Thank you. So
one more thing. I really think we have to impact on ethics. If we will put this impact on ethics, and we'll try to collaborate in intelligent way, and collaborate with human intelligent way to understanding the ethics, and some the same working in the same space, it will be a good connection. It will be worked.
Okay, great. So thank you for your
Thank you very much
for your answer to the question, and I think we will leave the next questions to the one-on-one session. Maybe it will be also easier for all of us to ask these questions more in private rooms. And the last presentation will be by Jan Klimaszewski, and he will present the paper entitled Versatile Robotic Workstation for Electronic Skin and Problems and Solutions. So Janek, the floor is yours.
Hi, my name is Jan Klimaszewski, and I would like to tell you about a few problems and solutions encountered in the development of universal robotic workstation for electronic skin. We are witnessing fourth industrial revolution, where collaborative robots have become one of the key pillars of development. Cobots are required to collaborate safely with humans in an intuitive and agile way. This could be achieved based on cobot sensors. One such sensor is the electronic skin, which can enhance human-robot collaboration through physical contact. One of the first problems my research team encountered while developing the electronic skin was designing a test bench suitable for electronic skin testing for multimodal measurements, for example, tactile pressure or proximity to human body parts. Therefore, my work presents the developed robotic workstation, which allows, among other things, the calibration of electronic skin, tactile measurements. In particular, the problems encountered when using a standard industrial robots are presented and ways to solve them are discussed. The presented approach allows for the automatic acquisition of many measurements of electronic skin sensor in order to, for example, test the sensitivity to touch or the possibility of estimating the distance to the approaching part of the human body. Initially, a robotic workstation was developed in terms of hardware. The main components of robotic workstation are a Fanuc robot with control cabinet, a reference device with a controller for measuring contact force, and the electronic skin with custom controller. The central device integrating the measurements and communication with the devices is a general-purpose personal computer. The general block diagram of the workstation includes not only the manipulator and sensors, but also the computing devices necessary for the operation of the entire workstation. After developing the workstation from the hardware side, it was necessary to perform software integrations of used components. This task was the main challenge of the development of workstation. Achieving appropriate result required the calibration procedure of the electronic skin reference frame in relation to the robot's base frame, the acquisition of the position of the robot's tooltip with the measurements from the electronic skin and the reference force sensor in a time-synchronized manner. The example developed application is designed to exert pressure on successive electronic skin sensors and simultaneously record measurements from all the devices. The robotic application consists of the robot motion program for executing of repetitive pressure trajectory on successive electronic skin sensors, robot client program for publishing robot position and measurements coordination, server program for measurements coordination, and finally the measurements acquisition program for acquisition of the electronic skin, the reference measurements, and the robot position with mutual timestamp. This figure shows 5 selected from total 288 successive electronic skin sensors measurements from the operation of an example application. Electronic skin pressure is in red, reference force in blue, and robot tooltip position is black. And this figure shows data from one selected pressure sensor. In summary, the proposed workstation meets all the requirements to provide electronic skin testing functionality in various scenarios, determining electronic skin characteristics for shear or normal touch force, estimating proximity, and much more. Workstation provides an example of integration of a standard industrial robot with robot operating system, commonly used in robotic research. It is a problem in itself. In the future, it is planned to replace the Fanuc robot with ES5 robot, which has built-in integration with robotic operating system. In order to further develop the workstation, it is worth solving the problem of manual calibration of the robot user frame against the electronic skin to further deepen the automation of the workstation. Thank you for attention.
Great, thank you, Jan. Now I opening the session, this part with questions and answers. So if you have any questions, please write them down in the chat. Okay, so while still waiting for some questions, I have one question. The proposed framework consists of the robot manipulator, right? So such manipulator, because of many degrees of freedom, even though we can say it's accurate, it has numerous inaccuracies and flexibilities, especially in the drives, that affect the accuracy of the whole system and the measurements. So can you explain why have you chosen such solution? Why, for example, we have some simpler and more compact mechanical constructions that can be used for the such skin, or even like the SCARA robot, for example, can be less flexible than the manipulator that you used in your research. So if you can explain why you have chosen such solution, or do you find any problems with that?
Okay, thank you for a question. Firstly, I think that the accuracy and the precision of this robot is sufficient for the task of measuring or calibrating the electronic skin, because it's stated in by the manufacturer of the robots. I don't know exact data, but it is below 1 millimeter of precision. So it is more than sufficient to exert, for example, pressure on selected electronic skin sensor. But we encountered problems with exerting few hundreds pressures on few hundreds of sensors, because although the first one was pressed correctly, the last one was often misplaced or mistargeted by a robot. But I think it's not a problem with a robot precision, but a problem with calibration of placement of individual sensors with respect to robot program or robot base frame. Okay, so I think in summary, I think the precision of this industrial robot and other industrial robots commonly used is sufficient for this task. Okay. And elaborating further, I have that robot in my laboratory, so I used what I have, and constructing some new devices would be waste of equipment which we can use, and and another topic that it is worth discussing is the robot stiffness, because and the whole robotic station stiffness, because while we measuring the pressure, the exerted force on of this electronic skin, it shows the stiffness can be measured and is shown in the measurements which we acquire, and this can be addressed in maybe in further research problems, but for now we try to measure the force, the reference force exerted on the skin, and the pressure response from the skin, and having these two values can compensate the stiffness or non-stiffness of the whole robotic station.
Okay, great. So thank you for this answer. I see that there are no further questions to this presentation, so I would like to thank all presenters, because this was our last paper in this session. So I really encourage you to go to reactions and maybe give some like high fives or some clap hands, or maybe the others, to encourage the people who are presenting for the questions in the private rooms. So this is from me.
Okay, thank you very much. We will open breakout rooms in a moment, and this will be the last part of our today's agenda. Before we finish, I'd like to encourage you to pin on the map, on the virtual map I mentioned. Also, we have our virtual mural. So if you haven't already put yourself picture of yourself or your surroundings, showing how you participate in MIDI, please do so. Okay, so like I said, breakout rooms will open in a moment. This will be the last part of the conference. We will see tomorrow. And now I would like to say goodbye in a special way, but I will have to join Wiesław, who is downstairs, and it will be a chance to also show you what's the weather. What's the weather now in Warsaw, and it's cold and snowy, so I have to wear cap. Okay, see you tomorrow.